Every day, we engage with articulated objects, turning the handle of an espresso machine, opening the microwave to warm leftovers, using a waffle maker or a mixer to prepare a meal, and even squeezing a bottle of ketchup onto a donut. Imagine you're an artist who has already defined the trajectory of an object for your animation. The next step is creating the hand motions that interact with the object, but traditionally, this requires tedious keyframing for each movement. We present an automated method to generate 3D bimanual interactions with articulated objects, producing a variety of hand motions for the same object trajectory. Very few prior works address 3D bimanual interactions with articulated objects. ManipNet generates natural hand manipulations but requires predefined wrist trajectories and does not support articulated objects. CAMS enables interactions with articulated objects, showing impressive results on the HOI 4D dataset. However, it relies on an initial pose, trains category-specific models, and focuses solely on single-hand motion synthesis. ArtiGrasp produces physically accurate bimanual motions using reinforcement learning. However, it relies on a reference grasp and cannot simultaneously relocate and articulate the object. We present a unified approach for bimanual interaction that is neither category-specific nor reliant on a reference grasp. In the first stage, our contact generation model creates bimanual contact maps. These maps condition the motion generation model and guide the sampling process. Finally, we apply optimization-based refinement to produce the final 3D bimanual meshes. We present two samples generated from the same object trajectory, displayed from two different camera views. We can generate challenging bimanual motions, such as passing the object from one hand to the other, guided by the contact maps. To show that we are not overfitting to the ground truth, we show the 5 nearest neighbors in the training set per test sequence based on object motions, with the first frame of object vertices centered at 0. Our generated test motions differ from the 5 nearest training ground truth hand motions. Our method also allows controllable generation. We manually specify contact regions using MeshLab and incorporate the binary masks using the in-painting technique during denoising. Our controlled result follows the specified contact regions. It differs from the uncontrolled generation and the ground truth corresponding to the same object motion. We present qualitative comparisons with existing methods. For a fair comparison, we condition MDMB on our proposed object representation. Leveraging contact maps, our approach produces more physically plausible interactions, even for objects with thin parts. OMOMOB enforces rigid contact constraints and fails to open the laptop naturally, while our approach generates dynamic and natural bimanual interactions, with one hand shifting from the side to the bottom to support the object, and the other hand opening the laptop cover. CAMS-B's stage-wise contact targets lack sufficient guidance for bimanual interactions, resulting in implausible outcomes. Next, we present ablations to examine the impact of our design choices. Incorporating global states is essential for generating physically plausible motions. Without it, the model cannot distinguish between a moving object and a stationary one. Without contact conditioning, the fingers fail to maintain contact with the ketchup bottle cap. Our optimization-based refinement reduces penetration, preserves hand-object contact, and improves overall motion quality. We demonstrate that our proposed part-based BPS features improve motion quality in the challenging scenario of articulating a ketchup bottle in an upside-down position. Our contact map guidance helps the predicted hand key points better align with the predicted contact maps, providing fine-grained adjustments that reduce penetration during the denoising process. we present results on the HOI4D dataset, demonstrating the versatility of our approach in single-hand motion scenarios. Notably, our model is trained across categories and generalizes to scissors and pliers with geometric variations. While our method generates plausible motions, it occasionally fails to maintain contact with objects that have very thin parts, such as a notebook cover. Minor penetration is observed, and the reasons are twofold: imperfections in the ground truth and limitations in our optimization-based refinement, which struggles to provide effective gradient directions in these cases. Incorporating physics-based modeling is a promising direction for future work. Using a model trained on the Arctic dataset, we generate results for the unseen partnet mobility dataset. While the presence of scissors in Arctic allows our method to produce relatively reasonable results for unseen scissors by following their articulated movement, it struggles with unseen pliers due to their distinct handle geometry, which differs from the training objects.